In this optimization problem, we have to find the dimensions of the largest rectangular enclosure. That means we're maximizing the area of a rectangle, and that we can make with 100 meters of fencing, given that the fencing for one side of the enclosure already exists. So let's start by drawing a diagram to visualize it. So we have one side of the enclosure already exists. So to make the rectangular enclosure, we only have to put in 3 other sides of fencing. 1, 2, 3. We have to find the dimensions. What we're looking for is the length and the width of this enclosure. Now, given that we have 100 meters of fencing, we'll need some of it for here, some of it for here, and then some of it for here for the third side. This is the other width that we'll have to do. We'll assume that the other length already exists. So we have our variables, width and length, and we want to maximize area, so we can come up with an area function. So we know that area of a rectangle will be length times width. Now the problem is we can't solve this yet because we have 2 separate variables. So we have to find some way to relate these 2 variables. So let's look for another function. Well, the distance around the outside where we're putting our fencing is the perimeter. So we can say that the perimeter of our fencing would be width plus length plus width. This side plus this side plus this side. And we know that that's going to equal 100 meters. So we can say that 100 equals 2W plus L. Just collect some like terms there and set it equal to 100. Now we can isolate our variable L here. That would be the easiest one to do. And if we did that, we would get 100 minus 2W equals L. Then we can substitute our value for L into our area function. And if we did that, we'd say that area is equal to 100 minus 2W times W. Now let's make it easier on ourselves. Let's distribute the W across the brackets, and that would be 100W minus 2W squared. A couple of things to note about our area function. It's a parabola because it's of degree 2. It opens down because there's a negative for the coefficient of that term. So if we were to sketch the graph really quickly, it would look something like this. We know that length and width have to be greater than 0 because we can't have a negative width or a negative length. So we're concerned with the region where area and width, which is our function here, are greater than 0. So that would be this area right in here. And we'll also notice that therefore we have some endpoints to our interval here. And they would be 0 and 50. And we know that because if width was 0 down here, length would be 100. And that would mean that this fence line would have to go right along the existing fence line, so our area would be 0, because if width was 0, then our area would be 0. Also at 50, if we plug that in here, we would see that length would be 0, and so in the other case there, if length was 0, area would also be 0. Now what we see is that we have a smooth continuous curve over that interval, and there exists, up at the top here, a critical point where the slope of the tangent line would be 0, and so therefore we're looking at a maximum. We also know that because it's concave down. So there exists one maximum value over that interval from 0 to 50, that what we're going to find out when we use some more calculus. So what we want to find out is where the derivative of our area function equals 0. And the reason is because the derivative means the slope of the tangent line at a given point, and that we want it to be flat like this where the slope is 0. Alright, let's get rid of some of this so we have some workspace. And let's find the derivative of area function here using sum rule and the power rule. So we would get the derivative being 100 minus 4w. Then we set that equal to 0 and solve for w. Move it over, that would be 4w equals 100, divide by 4, so w equals 25. So it looks like we'll have a maximum area when our width is 25. Now let's find out the length, because we want to find the dimension. So we can substitute w equals 25 into our perimeter formula here. And when we do that, we would get 100 minus 2 times 25 equals length. So 100 minus 50 equals the length. And so our length would be 50. So what we're saying is we'll get a maximum area when our width is 25 meters and our length is 50 meters. And that maximum area will be, if we just substitute it back into our original area function, will be 50 meters for length times the 25 for the width, which equals 1,250 meters squared. Now let's just confirm that it is indeed a maximum. I'm going to go here and show a plot of our function. This is our area equals 100 minus 2w squared function. So our vertical axis is area and our horizontal axis is the width. Our critical point exists right here where the slope of the tangent line is 0, and if we extrapolate that down, we can see that it's at where width is 25. And that will lead us with an area of 1,250 meters squared. And if we pick some points to the left of our critical point, let's say 10, go up to our curve, draw in a tangent line there at the point 10, you can see that it's positive. And if we went to the right, say 40, went up to our curve and looked at the tangent line there, we can see that it's negative. So our tangents are increasing on this side, flat at that middle point, the critical point, decreasing on the other side. Therefore, we have a maximum. And we also know that because we're concave down here. So we've confirmed that we have that one maximum over that interval. Okay, so let's come back and just summarize and answer the question. So we want to find the dimensions of the largest rectangular enclosure we can make with 100 meters of fencing, given that one side exists. Well, the largest we can make is when length is 50 meters and width is 25 meters. And there you go. Oh, and one more thing we can say. For this scenario, where we have an enclosure, rectangular enclosure with 3 sides, the largest area we can make in that scenario is when the length is twice the width. And that will be true regardless of how much fencing we're going to use.